The CO₂ networks are district heating and cooling networks in which CO₂ is used as a heat transfer medium instead of water. Apart from a few prototypes, these innovative systems are still in the early stages of development. The potential of such networks has already been demonstrated in research projects, but the challenges lie in the details. Compared to conventional district heating and cooling networks, CO₂ networks offer several advantages. The network can be used as a district heating and district cooling network. No parallel infrastructure required for heating and cooling. Heating and cooling can take place simultaneously. Due to the low system temperatures, low temperature heat sources can be integrated efficiently. Pipe diameters are approximately 3 times smaller. No insulation of the pipes is required, and there are several economic advantages. The CO₂ network is designed to utilize the phase transition and the associated enthalpy of vaporization. The network therefore has a liquid and a gaseous line. Which of these is the supply or return line depends on whether the CO₂ network is operated as a district heating or district cooling network. The network temperature is between 10 to 15 degrees Celsius, which is associated with a pressure of around 50 bars. The CO₂ network has a central heat source or heat sink, for example, a lake, a river, or geothermal energy. These low temperature sources have the advantage that they can often be utilized at no cost. Connection to a conventional district heating network is also possible. In cooling mode, this can even be used as a heat sink so that the surplus energy can be fed into the district heating network. The network also requires a central CO₂ compressor, which ensures that the pressure in the gases is high enough to prevent condensation. Heat pumps are required for decentralized transfer stations, consumers, in order to raise the temperature to the required level during heating operation. In many cases, cooling can take place directly. A pure cooling consumer does not necessarily need a decentralized heat pump. If temperatures below 10 degrees Celsius are required, a decentralized heat pump can be used to lower the temperature. Other low temperature sources can easily be integrated into the network. The CO₂ network can be operated either as a heating or cooling network. When operated as a heating network, the gaseous pipe acts as the flow. The energy is taken from the gaseous pipe and fed into the liquid pipe. In operation as a cooling network, this is reversed. The liquid pipe is used as the flow cooling source, and the gaseous pipe is used as the return. Simultaneous operation as a heating and cooling network for different consumers is also possible. What are the challenges in operating CO₂ networks? Due to the high pressure level, there are high control requirements to be observed. Control is significantly more complex than with conventional district heating networks. Selection of suitable pipes. There are only a few suppliers offering flexible plastic pipes that are suitable for pressures in the range of 50 bars. High investment costs are the consequence. Steel pipes would in principle be better suited to high pressures, but are unfortunately much more complex to install. A trade-off between pipe costs and excavation costs is required. Therefore, several simulation models are developed to investigate the different operating modes in a CO₂ network. In operation as a direct cooling network, in operation as a district cooling network in summer and heating network in winter, in operation as a district cooling and heating network at the same time. Furthermore, the utilization of free energy sources, lake, river geothermal energy, and the connection to a conventional district heating network are investigated. As part of the project, the detailed design of the transfer station will be developed. In addition, a techno-economic assessment of CO₂ networks will be carried out in comparison to conventional district heating and cooling networks.